Yeah. Comes on, everyone. What happened today? No one is there. What happened, everyone? We went to some movie. Extra class. Counts extra class. Which subject? Physics. Rotation not yet finished. So they can attend this now. We are doing rotation only. Gods. अलग ही लेवल है उनका. ठीक है. ठीक है. Let's start off. Switch on your cams. Recovered a bit. So let's start off with angular momentum. Quite an important thing. If it is a rotation only, they should have attended this, but okay. Maybe pace people will scold them, I guess. Or maybe they're scared. Vijit is not scared. Ah, Vijit. Neil, cams on, Re. Udi and Vartika, cams on. If someone is attending both the classes, then you just let me know. Someone said they'll do that. Said I'll attend both the classes. In your class, I'll keep your cam off. I said, that's okay, you can do that. Your seniors used to do that in COVID batch. Yeah, 54, 55. Let's go. Like I said, we will focus more on calculation of angular momentum, and we will do little conservation also. I didn't expect so many people to miss. Problem kya hai na? We can't even cancel because we won't get another slot. Timings won't match for everyone. That is a headache. ठीक है. Okay. A 2 kg mass moves along 3x plus 4y is equal to 1 with speed to 10 meters per second. Find magnitude of angular momentum about 1, 2. Let's get this. What happened to Utsa? Not well. You don't have glasses. Maybe that's why you're looking weird. Comes on, everyone. A 2 kg mass is moving along 3x plus 4y is equal to 1 with speed 10 meters per second. Find the angular momentum about the point 1, 2. How do we find this? So let's say if you have a line ax plus by plus c is equal to 0. And if you have a point x comma x1 comma y1, this would be the perpendicular distance. Hope everyone remember straight line ka formula. In case you don't know, remember this. So perpendicular distance is given by ax1 plus by1 plus c by root over a square plus b square. Know this thing from straight lines? This is the perpendicular distance between a point and a straight line. So the perpendicular distance here will be A is 3, x is 1, 4, 2 minus 1 by root over 3 square plus 4 square. That guy would be 3 plus 8, 11 minus 1, 10 by 5, 2. Therefore, angular momentum is m, r perpendicular into v, m is 2, perpendicular is 2, and v is 10. 40. Check. Make sense? Easy? Check it out. If someone gives you a line and asks you, and if you observe here, it's constant actually. The reason why I asked you magnitude is because when I say velocity 10, I didn't tell you which way it is going. It could go this way, it could go this way, right? So I can get plus cap or minus k cap. Both are possible. But it will be a good theoretical equation. If a particle is going in a straight line, then the angular momentum is what? Constant. It doesn't matter how far it goes. Perpendicular distance remains same. Clear? Next one. Easy? Next one. We have a particle here, mass m, going with speed v, parallel to x-axis. This point is your origin, 0, 0. This point is A, which is 0, 2D. This point is B, which is 3D, minus D. This point is C, which is minus 2D, 3D. So there are 4 points like this. Find angular momentum of this particle about ABCD. Find L bar about OABCD. OABC. Let's get this. Particle of mass m is going with speed v, and there are 4 points O, A, B, C. So depending on where you're standing, you'll get different angular momentums. Find the angular momentum. Okay. See, check your answers. First one. This is how you do. This is going with V, mass m, extend the vector. This is O, drop the perpendicular. This guy will be 2D because that coordinate is 0, 2D, right? So angular momentum about O will be m, V, perpendicular distance 2D. And if you see the rotation, this is your R perpendicular. This would rotate this way. The velocity would have pushed the rod to the right side. That is anti-clockwise. So that would be minus k cap. Angular momentum about A is 0 because it is passing through the axis. This is going with V here. This guy is 0, 2D. Where is B? B is 3D, minus 2D. There is this guy, minus 2D, 3D. That is C and that is B. Same story. Extend the vector, drop the perpendicular. This distance will be 2D plus D, which is 3D. This distance will be 3D minus 2D, D. So L about B will be Mass, velocity, perpendicular distance 3D, and if you see the rotation would be minus k cap. Angular momentum about c, m, v, perpendicular distance d. Now, if you observe here, this is r bar, it would have rotated upward. That is plus k cap. Magnitude, I'm sure you're confident, but direction, be careful. Please check it out. Ask me if you're confused.
So you took minus k cap into the plane, right?
Ha. Out of the plane is plus k cap. Ask for anyone confused. It's important. You should know how to calculate angular momentums. Clear? Any doubts on this? Udayan, clear with this? Vartika, got it? Molika, clear? Anyone has a doubt? Ali, clear with this? Neil, next one. Going ahead. Next thing. If you take purely rotating bodies, Vijit, clear now? Got this right. Like I said, you should know how to calculate first. So if you take purely rotating body here, and if this guy is rotating with omega, same story. Consider a particle mi going in a circle of radius ri. Vi, which will be ri omega. The angular momentum of this particle will be mi, vi, ri, which is mi ri square omega. So L bar about the system will be sigma Li, which is sigma mi ri square omega. And if you observe, this term keeps popping up everywhere, sigma mi square. So angular momentum about an axis is given by the I about this axis into omega bar. This is for pure rotation. If a body is purely rotating, you can take angular momentum like this about the axis. If you observe, it kind of looks like P is equal to mv. M ka place mein I and V ka place mein omega. Hope you can see the resemblance. The same thing you could have done for this also. And now, if you remember, we did this in energy, degrees of freedom. If a particle is going Vx, Vy, and Vz, the angular momentum for the translation will be m r center of mass, V center of mass, where the velocity of center of mass would be Vx I cap, Vy j cap, and Vz k cap. Takes care of the translation. Similarly, you can also have three rotations. So let's say this is your y-axis, x-axis, and z-axis. The rotational angular momentum, that would be I x omega x, I y omega y bar plus I z omega z bar. You have to add them vectorially. So just like in energy, you can also have angular momentum in different directions. Now in this, rolling is a special case where you have one translation plus rotation. So you can't, I'll show you in the next page. Have a look at this. Anyone not clear with anything on this page, please ask.
So if the body is translating as well, then can we write that MBR part separately along with the pure rotation part?
मतलब it is अभी नहीं वही करेंगे next. मतलब if you have translation plus rotation then add करेंगे ना.
Okay.
L of a system will be translation plus rotational components. Sometimes you will see what there is no rotation, there is only rotation plus rotation. It could be combination of everything. It is. So if you want me to say that, I'll write it down. So L of a system will be L of translation plus L of rotation. Fair enough. That's what you wanted to ask. Is that what you're asking? No.
Yeah, I was asking if you could get to that.
हाँ वही है ना टोटल तो वही होगा वेक्टोरियल ऐड करना पड़ेगा
ठीक
clear everyone next one Neil clear with this angular momentum of a rolling body so if you see a rolling body is nothing but a translation plus one rotation you can assume everyone is going with V so one is rotation so we can say angular momentum of a rolling body is angular momentum of center of mass plus angular momentum about center of mass just like energy so this would be mr so you treat the center of mass like a particle and find its angular momentum plus I see you stand on the center of mass and find the rotational angular momentum. But remember, only valid for a rolling body. Have a look at this. Clear? Maulika, got this? Going ahead. The relation between torque and angular momentum. If you see the resemblance, it kind of looks like, torque is nothing but rate of change of angular momentum. Doesn't this similar to force is rate of change of momentum? Newton's second law. Now from here we know for purely rotating body, this is I omega by dt. Product rule, this will be omega I d omega by dt plus omega di by dt. This is the actual formula for torque. Again, for purely rotating body, we are writing this. Yeah, we can write this in general for anything. Now, if I is constant, then the term di by dt becomes 0. Then the equation becomes torque is equal to I d omega by dt. And d omega by dt is I alpha. So this equation I is torque is equal to I alpha, which we are using, is only valid when I is constant. Till now, we never had a problem, where I was changing, so it didn't matter. But yeah, we will see a problem where, when I changes, then you can't use torque is equal to I alpha. And from here, you can see if torque about an axis is 0, then angular momentum about that axis is constant. That is L initial is equal to L final. This is your third conservation, law of conservation of angular momentum. If you think about it, till now, this is the third conservation. The first one was energy. To conserve energy, what should be 0? Work done by external force. To conserve momentum, linear momentum, what should be 0? External force. External force. So to conserve angular momentum, torque about an axis should be 0. So when it comes to angular momentum, you have to be careful. You have to ask yourself about which axis is the torque 0. You can't conserve about any point you want. You have to find a point about which torque is 0, and only about that point it will be conserved. This is your third conservation. Have a look at this. Clear? Any doubts on this? Turn in the page. Vartika, clear with this? Aryan, Aditya, Ali, Udyan, Neil, clear. Now, the same thing. When you wrote torque is equal to dl by dt, this can be written as integral torque dt gives you change in angular momentum. This is also called as angular impulse. If you remember, you had something called impulse. This was change in linear momentum. So there, linear impulse, right, is like someone kicking. Here it is someone is kicking in such a way it is rotating. So that means you can write this thing torque. So delta L bar torque dt, torque can be written as R bar cross F dt, where F dt becomes linear impulse. This is the relation between angular impulse and linear impulse. R bar cross J bar. So example, if you write change in angular momentum about center of mass will be R perpendicular. This is the perpendicular distance from center of mass into J. We will see these problems later on. This is the relation between linear momentum, angular impulse, and linear impulse. And if you try to plot a graph between torque versus time, this is the positive area and this is the negative area. So area is torque dt. This gives you again change in angular momentum or impulse. You can see the resemblance. It looks quite similar to FDT graph. Have a look at this. So whenever someone says impulse, right, think of like this. When you're playing carom board and you hit a striker, that's an impulse. When you punch your friend, that's an impulse. When your mom slaps you, that's an impulse. So easy to remember. Clear with this? Let's see some problems now. Next one. A particle of mass m is projected with speed u and angle theta. This is origin. Gravity is there. Find angular momentum about the origin as function of time t. Particle of mass m is projected with speed u and theta, projectile motion. So find the angular momentum as function of time t. It's a particle. So remember, for a particle, what do you use? MR cross V. Purely rotating body, I omega. Rolling body, angular translation plus rotation. If you have another system which is having double rotation, then rotation plus rotation components. We'll see those examples also. So this is simply a particle. There are two ways you can do this. Try. Remember the formula MR cross V bar. I hope you remember what is R bar and V bar for a projectile. Just do a cross product. Why HY? That will be too long, रे Arjun. HY का problem होगा, God. I'll tell you one thing. The mistake with that will be velocity ऐसा होगा. Then isn't the perpendicular distance this?
Oh yeah.
Brute force everyone. What is R bar? U cos theta t I cap plus U sin theta time minus half GT square. You should know your formulas. Velocity vector would be U cos theta I cap plus U sin theta minus GT j cap. Oh yeah, now then angular momentum will be MR cross V. Just do the cross product. Iska, there's no use in using 2 into 2 that use mat karo, determinant. You can simply do no I cross I is 0, so this is gone. I cross J, J cross I, That's it. There's only two terms. Only if you have IJK, use 3 into 3 det, or else it is waste. You can just cross multiply and finish it off. Get me the answer. You get a good answer. Narian, that is wrong. You get proper single term answer. Next thing. आया आंसर किसी को? You get minus mg u cos theta t square by 2 k cap. Clear? That's what you should have got. Now there's a better way to do this. This is fine. You can do this. I could do this in a minute. You should be able to do this. Simply cross product. But an alternative way is there. Alternate is this thing. Particle is projected with u and theta. As this is flying here at any instant, if you observe, the weight is mg. There's only force acting on the particle, isn't it? Extend the vector, drop the perpendicular. This guy would be u cos theta into time. So torque will be mg into u cos theta into time. And what is change in angular momentum? Integral torque dt. This is minus k cap. So this would be mg u cos theta t dt from 0 to time minus k cap. This would be mg u cos theta t square by 2 minus k cap. That's your answer. Faster. If you can calculate torque as function of time t and then just integrate. Making sense? This is faster. But हाँ वो click होना चाहिए boss. I can do with torque. Click नहीं होता है कभी कभी. Exam में तो it doesn't click me. So then just keep quiet and just solve. That's what I'm saying. You should have a calculation speed. Then it doesn't matter. When ideas don't come, then speed will compensate up to an extent. Check it out. You can do either way. Both will give you the same answer. Any doubts? Anyone not convinced with this? Malika, clear with this? Any doubt? Please ask. Don't hesitate. Let's see one more. Next thing. We have a disk M R This is going with V, and this is rotating with omega. This is point A, which is right below this. This is point B. This is point C, and this is point D. This distance is r by 2 and r by 2. It's a rotating disk. Find angular momentum about ABCD. We have a disk going with V and omega. Find the angular momentum about these 4 points. This is translation plus rotation. It's a kind of the angular momentum of a rolling body. Should I show you one? I'll help you with one. See. So first thing, if I talk about A, this is going with V. This is point A. This is center of mass velocity. So drop the perpendicular. This is R, and this is omega here. So angular momentum about A would be angular momentum of center of mass, meaning you treat the center of mass like a particle. Plus about center of mass, go and stand on the center of mass. You will think it is in pure rotation. So this is M. R perpendicular is R. V direction is minus k cap. Plus ICM omega, that is mr square by 2 if you stand on the center of mass, into omega, the rotation is plus k cap. Please check the directions. There's no relation between B and omega here, so answer is that's it. Same thing, if you try to do for B, in this case, the translation component is 0 because the velocity is passing through B. There'll be only the rotational component, mr square by 2 omega k cap. There's no translation angular momentum about point B. Please check. Do for C and D. Try. I'll give you a minute. Let's see. Look at C and D. Check your answers. L about C, the perpendicular distance is M. R by 2. V, direction would be plus k cap. The rotation part will always be same. Check. What are changed? Rotational component will be same. The second term. Which one you're saying, right?
सर वो R by 2 नहीं होगा, वो MR square by omega by 2 वाला जो है।
क्या था फॉर्मूला? ए बोर्ड सेंट्रोमस मतलब क्या? आई सी ओ एम ओमेगा ना.
हाँ,
यू
ओके,
ऑलवेज स्टैंड ऑन सेंट्रोमस रिकॉर्ड.
राइट, ओ गॉट इट।
तो सेकंड पार्ट तो कहीं पे भी यू सी डजंट मैटर, यू ऑलवेज कम टू द सेंटर ऑफ द डिस्क ओनली.
ओके, गॉट इट।
क्लियर? ऑल गॉट दिस? लेट्स सी वन मोर लाइक दिस. हाँ उदयन, क्लियर ना कैलकुलेशन कैसा करना है? मौलिका, क्लियर? Same thing, top view. We have a rod here, mass m, length L, going with V and rotating with omega. This is point A, this is point B, where this distance is L by 3, and this point C. Find angular momentum about ABC. This is your center of mass. Clear? Same thing. This is like your pen game. The pen on a table and you hit it, so it is translating and rotating. Find angular momentum about ABC, 3 points. A and C are corners, B is somewhere in the middle. Check your answers. MVL by 2 minus K cap plus ml square by 12 omega plus K cap. The second term will always be same. Easy? Check. Anyone who didn't get the term, direction, anything not clear, please ask.
So if they ask us for magnitude, just the plus k cap minus k cap.
हाँ इसमें तो सिर्फ हाँ just start कर लेना
Okay.
with signs. Yeah. Clear? Going ahead. Next one. Vidyut, go ahead. We have a particle, mass m, theta, and this guy is going in a circle with speed v. It's a called conical pendulum. We have done this in circular motion, if you remember. Particle goes in horizontal circle. Gravity is there. We have point O here and O dash here. O is the center of the circle. O dash is the point of suspension. Find angular momentum about O and O dash. What's the answer? This is a good one actually. On this, we can frame a question, on a more than one choice, man. We can get a good question on this. Just calculate and just get some water and come. Let's see. what are you calculating रे इतना बड़ा बड़ा आंसर्स नहीं आएगा. See, first thing about O, right? This is your velocity vector. This is your R bar. They're already perpendicular. So L about O will be M. R is L sine theta into V. Bus. Because this is the radius L sine theta, isn't it? From the distance from O to that is already perpendicular now. And what about the direction? It is going in a circle. So if you observe here, velocity is this way, R bar is this way, so L bar is upward. So as this guy is going in a circle, the angular momentum will be up, like this. So it is constant actually. So angular momentum about O is constant. So you can actually see the reason why it is constant also. If you look at the FBDs here, we have tension, we have mg. This is over here. If you look at the components, this would be t cos theta and this would be t sine theta. So here t cos theta will balance mg, so they will cancel out. And t sine theta passes through O. Therefore, torque about O is 0. Since the torque is 0, angular momentum is constant. Therefore, torque about O is 0. Therefore, L bar about O is constant. Now you'll understand why I'm doing this. Something interesting happens with O dash. O dash is goofed up. So simple question would be this. Is angular momentum about O constant? Angular momentum about O dash constant? Calculate for O dash. You just try to find the point and take a perpendicular distance and finish it off. Show you. Yeah. So how does that look? See. So this is your O dash. Look at the velocities, how it is. This is your velocity. This is your R bar. Aren't they already perpendicular? The string is already perpendicular to velocity. And if you do R cross V, the angular momentum would be actually this way. So angular momentum over O dash would be M L V. But the problem is the direction. It is always, like this. It is at an angle. It's like a crown shape. The magnitude is constant, but the direction changes. So if you the vertical lines, so this would be 90 minus theta. So this angular momentum has two components, L cos theta and L sin theta. So if you look at this angular momentum of this vector, this is what you'll observe. There is one L sin theta component, which is constant. And there is one L cos theta component, which is rotating. This is your variable component. Magnitude is constant, but direction is changing. So here, if you see LO dash, magnitude is constant, but direction changes. And even in that, you'll observe the component of angular momentum is again constant. There is one component, L sin theta will remain constant, but L cos theta will change. An interesting thing here, if you look at the torque actually, O dash, this is mg, and this is tension. If you drop a perpendicular, and if you try to take torque from here, this is the perpendicular distance, that is L sin theta. We have torque about O dash will be mg L sin theta. And the other interesting part, this torque direction is also changing actually. And how is this torque direction? Isn't it rotating this way? This torque direction is like this. The torque direction is this. Torque is always along the circle. Torque is also not constant. At different positions, you have different torques. Torque is along the circle. So this is what you will see interestingly here. This is the torque. This is your R bar. This is your velocity bar. And this is your L bar. So if you see, torque and angular momentum both are perpendicular. Torque is perpendicular to angular momentum. This kind of looks like force is perpendicular to velocity. Think about uniform circular motion. If force is perpendicular to velocity, what happens? Your direction changes, but magnitude remains constant. You go in a circle, isn't it? Something similar happens. Now, see, I'll tell you one thing. Technically, it is difficult to visualize what the hell is happening. Mathematically, it makes sense. Because the torque is perpendicular to L bar, the magnitude remains constant, but direction changes. Just think of it like a uniform circular motion. Because if you apply torque, angular momentum should change. But if it is perpendicular, you can't change the magnitude. That means the only way you can change it by changing direction. And that is the reason L bar is rotating in a circle. Torque is also rotating in a circle. Torque and L bar are always perpendicular. This is a very important one. So let me show you how they'll frame a more than one choice question on this.
Sir, this is always true.
Which one? If torque is perpendicular to L bar?
Yes, sir.
Obviously, ना सोचो ना अगर torque perpendicular हो गया, you can't change magnitude. To change magnitude, there should be a component along the Rehan, think in terms of force and velocity. वो easily visualize हो जाएगा. If there is no force along velocity, why will the magnitude change? So same way, if there's no torque along L bar का direction, why will magnitude change?
Yes, sir.
Remember, हमने center of mass में rocket propulsion problem किया था last में. The thrust force was always perpendicular to velocity. Speed of the rocket was never changing. That way. I disconnected when you wrote L is equal to ml. देखो ना, when you're taking angular momentum from O dash, this is your R bar, right? The line from the O dash to this thing. So that is R bar. This is velocity. R in the already perpendicular. तो MLV ना directly. उसका कुछ component गिम्बलेंट कुछ जरूरत नहीं था. All clear? Now, how will the question be framed? See, this is how they'll ask. They will say, for a system, if torque is given by A bar cross L bar, where A bar is a constant vector. Options will be like this, but they'll give this much only. They will say angular momentum is constant. Mod L bar is constant. Component of L bar along A bar is constant. Angular momentum और क्या कर सकते हैं? Torque is changing. L bar is variable. You can keep asking all that stuff. Now, if you relate this to our question here, this is how it would look. So when this guy was going in a circle, if you observe, this was your L bar. This was your A bar. This was your torque. This was 90 minus theta. So there was a component here, L sine theta, and there was a L cos theta. And observe here, see, if you do cross product, if you say torque is equal to A bar cross L bar, does it mean torque is perpendicular to L bar and torque is also perpendicular to A bar? Cross product, no? If torque is perpendicular to L bar, what will happen? L bar can't be constant. Magnitude is constant. L bar is variable. Torque is changing. Component is constant. This is exactly this question here. So A bar is a vector in the mg direction. So here basically A is in the direction of mg. So no matter how much you rotate, A bar will be up only. This is your A bar. This is your torque. And this was your L bar. Torque is perpendicular to L and torque is perpendicular to A. And the component of L bar along A bar will be constant. The other one is rotating. L cos theta rotates, L sin theta remains constant. This is how they'll put this question in advance. Have a look at this. Clear? Maulika, Vartika, clear with this? Rehan, Aryan? It's a good one. Next one. Next one is kind of little out of portion, but advanced paragraph they can ask. Mains they won't ask, but advanced they can ask in a paragraph. They'll explain you a bit and they'll expect you to solve. Yeah, it's not like something different. Problem is it is on the border of you can figure it out. The swinging table fan wala. So we have rotating with omega 1, mass ml, the rod, disk, mass m, radius r, and this whole guy is rotating with omega 2, and gravity is there, and this whole setup is rotating in a circle. First thing, find angular momentum of the system. That is fine. That much you can handle. Find omega 2. Find relation between omega 1, omega 2. If the rod does not fall down horizontally. Find relation between omega 1 and omega 2 if rod remains horizontal. Think about it. If there's a gravity, shouldn't the rod just become like this? But for some reason, it is not. Let's do the first one. B, I'll tell you. There is a possibility of rod going off like this. Rod can swing down due to gravity, but it is not happening. Get the angular momentum. That's the easy part. We have done something similar in energy. This is a double rotation. You can't use a translation plus rotation. Rolling body ka formula you can't use. Remember, there'll be two angular momentums. One is rotation, one is revolution.
So about the axis of rotation only, right?
System, matlab about this main axis.
Okay.
show you. Try, I'll give another 30 seconds. नहीं Ali, that is wrong. एनर्जी नहीं है, यू कांट ऐड डायरेक्टली यहाँ पे आई कैप जे कैप जैसा आएगा. See, might be right, Arjun. देखते हैं. So first thing, this one, when you're rotating with omega 2, so this angular momentum, let's call it L1, will be mr square by 2 omega 2. Let's call it L2 actually. Now, what about the direction here? Now, if you see this direction, right, it is not constant. L2 is like this, away from the center. So this is a variable component here. The second one, you're rotating about this guy, omega 1. So first about this axis will be mr square by 4. So this angular momentum L1 bar, and the rod is also there here. The disk will be mr square by 4 plus ml square, parallaxes theorem. This is for the disk. Plus rod is ml square by 3. This is for the rod. We had done the same thing in energy. So I omega 1, and this car direction will be constant. This L1 is upward. So that means this system actually has two components of angular momentum. One is changing and one is going up. And if you see, both are perpendicular. So if someone asks you find the magnitude, you have to square them and add them. It's a vector quantity. Similar question asked in 2016 May. That is slightly more complex, but it was like this. And this whole setup was rotating in a circle. Idea same tha. So this was one rotation L1 bar and this was L2. They had to take components L2 plus L1 cos theta and L1 sin theta and then square them and add them. So it was a double rotation. So they did ask, even though portion may mention nahi kiya tha, they were asking questions of this sort. So here I gave both the things are perpendicular. They gave at an angle. So end of the day still vectors. Have a look at this. We have done the same thing in energy. L1 parallaxes theorem na God. This is ml r square by 4. Array rotation में किया ना energy में. You guys are not revising notes. That's why you're asking. Perpendicular axis theorem, mr square by 4 plus mr square. Same to same question किया God. कहाँ पे था? Don't forget important questions. Why do you think I keep telling you guys to revise multiple times? देखो. ठीक है? I1 and I2. Then use vectors, na God. If two vectors are not perpendicular, you don't know how to find magnitude. Yeah? If I give you A and if I give you B and theta, don't you know how to find magnitude? No, don't know. A plus B cos theta and B sin theta. Then square them and add them. Components से निकालो ना. उसमें क्या है? That is fine. You guys are gods, रे. You guys understand angular momentum, but vector direction confuse हो जाते हैं. होता है. Happens when you understand big things, small things get confusing. Let me show you something. So this question is still not over. We have to find the relation between omega 1 and omega 2. But before that, let's see something.
I am here at the University of Sydney, where the mechanical engineering shop has horizontally with just one hand at this end. It is impossible, okay? Now I'm gonna let go. You gonna be able to hold this at all?
I've shot.
Can you lift it out? Make it horizontal. Hold it. Come on, just try to. I want you to hold it out horizontal. See if you can. Hold it. Oh, come on.
So you can see it is pretty heavy. It is almost 20 kgs. So lifting it horizontally is very difficult. So if you see the disc it can rotate. This is called a flywheel. So this is what I was showing, a rod with a disc rotating disc.
What I'm going to do is I'm going to spin this up to a few thousand RPM, and then I'm going to attempt just that, to hold it from one end and have it out horizontally. Five, four, three, two, one, boom. I'm going to let go of my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there. It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel...
If you see, the moment it starts rotating, it actually becomes quite easy to lift. Now, this thing is very difficult to explain in terms of forces and stuff, but mathematically it will make sense. What is happening? The mg ka vector is trying to pull it down. Tell me one thing, what does a torque do? Torque will change angular momentum. So here, because that wheel is rotating, observe one thing, he can't keep the thing at rest. He will always go in a circle.
Down to the ground as you'd expect. The weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyro.
So if you observe, he can never be at rest. Because wo rotating disc jo hai, that angular momentum component is changing because of this mg. The moment he tries to keep it at rest, it will fall down. So there are actually, if you observe, there are double rotations here. The disc is rotating about itself and the whole system is rotating about this person. This was the same question we are doing right now.
Gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme. I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck. But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning. Let's prove that I could lift it just this end without it spinning. Here we go. I mean, it's just kind of awkward with the hand.
Careful. Careful.
That's almost 20 kgs of weight. And see, where is he catching it?
Barely. Oh, goodness. Do you even lift? Clearly, I do not. Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success. Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go! That was
Now
perfect. Now I'm going to
And see, where is he catching?
release my left hand, and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1.
If you observe, right, he can never keep it at rest. The moment he lifts it, he can lift it, but it will start spinning in omega 1. Because if it doesn't spin, the angular momentum won't change. If the angular momentum doesn't change, then the torque due to mg will make the rod fall down. So mathematically, I'm sure it is making sense. Torque is there, that is changing angular momentum. But in terms of forces, it becomes very difficult to visualize, because if you try the FBD right now, the rod ka weight is mg down. That means the normal reaction on his hand should be n, which should be equal to mg. But that means he's actually lifting a weight of 20 kg. But in the beginning, he was struggling, isn't it? Now he's not struggling. Something is goofed up. Matlab, we are not able to figure this out. Kya ho raha exactly? So this is there. It's very difficult to explain in terms of forces and stuff. But this is what I was saying, last time. Like, people find angular momentum more tough than quantum mechanics. It goes out of the mind. Mathematically, it makes sense.
Nice. 3, 2, 1. It feels incredibly light as I do that.
So if you think about it, maybe, the ancient weapons, we talk about it, right? We say, the king must have lifted a big gada, which has weight of 200 kg, 300 kg ka thing. So maybe they had a rotating system inside it. Before lifting, he starts the machine, it rotates, and then he lifts it. Who knows? Maybe weapons are made that way. This is what I keep saying. When you take science to extreme, it looks like magic. So now we need to solve. So what is the rotation omega 2 so that this thing doesn't fall down actually? Right? So think about that. We will do after the break. Come back by 7:05. Any doubt so far? Anything you're not clear, please ask.
But I had a doubt in question 60.
Question 60. Bolo.
So with respect to B, this is the same as with respect to the origin.
Origin nahi hai. B is here, na? See, this is the center of mass, na? It is passing through B, right? So transition component is 0. MR perpendicular B, there's no perpendicular distance.
Okay, sir.
That way. This is it is like origin nahi hai. Matlab, if velocity is passing through this, so we ignoring it. और कुछ नहीं था. ठीक है?
Yes, sir.
Others? Anyone else has anything else in the notes? ठीक है. Come back by 7:05. Oh, it's only 6:55. Yeah. Okay, come back early then. How are you getting the directions? Right hand thumb rule, now. And देखो ना, if it is rotating like this, if you rotate your thumb, isn't the thumb pointing outward?
Yeah, sir. Positive x-axis.
And then अगर ये ऐसा rotate कर रहे, isn't the thumb putting upward? So basically, it's all thumb. So, let's see how to do this now. So, the one thing is clear. So when this guy is rotating here, we have an angular momentum L2 bar which is changing. L1 bar plus L2 bar. This is constant and this is variable. The torque is equal to dl by dt. Since L1 is constant, we just try to take a L2 by dt. The problem is what L2 ka magnitude, so I know the direction looks different. So what we do, this is how we take care of it. See, if I show you in the top view, this is the same technique we used in the last class, for the disk to find alpha. This was X. This was Y. This was the disk. So this was your L2. Let this be angle theta, and here d theta by dt is omega 1. Because this whole thing is rotating with omega 1. So L2 bar will be L2 cos theta I cap plus sin theta j cap. And if you differentiate this dL2 by dt, we get L2 minus sin theta d theta by dt I cap plus cos theta d theta by dt j cap. And what is L2 we calculated here? R square by 2 omega 2 and d theta by dt1 is omega 1 minus sin theta I cap plus cos theta j cap. That's your rate of change of angular momentum. Now, for this rod, if you look at the forces acting on the system, this is a disc ka weight mg and rod ka weight is mg. So torque about the axis is mg L by 2 for the rod and mg L for the disc. And this should be equal to dL2 by dt. So this will be 3 mg L by 2 should be equal to the magnitude mr square by 2 omega 1 omega 2. Therefore, omega 1 omega 2 will be 3g L by r square. That's your answer. Take it out. You can see what we did. First thing, we calculated the angular momentum L1 bar and L2 bar. In this, L1 is constant and L2 bar ka direction is changing. So basically, the mg ka jo bhi torque tha, instead of making the rod fall down, it is being used to change the direction of L2 bar. So how do you find L2 bar ka differential? Assume after some time it has rotated theta, then the rate of change of angular momentum, this will, L2 bar will be L2 cos theta I cap sin theta j cap differentiated. Then you get this thing. And this should be the torque about the axis, which is mgl by 2 and mgl. Equated and you're done. Check it out. This method, right? I taught you in the last class. This guy, which one? This problem, if you remember. To find alpha, हमने same logic use किया था. We found omega rotating with theta and then we differentiated it. Same thing you're doing for angular momentum here. Check it out. It's a pretty good one. This is the reason why it is not falling. Mathematically, it makes sense. In terms of forces, it's very difficult to explain what the hell is happening. Clear with this, everyone? Understood how we did this? This is a technique you should know to, find if something is magnitude is constant but direction is changing. This is how you find the rate of change. Because if you just try to differentiate the magnitude, you'll get 0. That doesn't make sense. Clear with this? Next one. Arjun, Aryan, clear with this?
Yes, sir.
Sir,
Okay.
sir, here you took components because the direction was changing.
Yeah. My logic है ना देखो ना यहाँ
Is changing. So what is changing is a I cap J cap, na? See, this magnitude is always L2 only. It's a unit vector. So whenever someone says magnitude is constant, direction is changing, this is the way to do. All clear with this? Let's see next one. Going ahead, Utsa, clear, na? Correct. We have a rod here, hinged at one end, mass m, length L. On top of this rod, there is an insect. Mass m, going with speed u. Speed of insect with respect to rod. Gravity is there. But what people observed when this insect is moving, right, the rod is rotating with constant omega. Technically speaking, shouldn't the rod fall faster and faster? It is observed rod rotates with constant omega in the vertical plane, even though there is a gravity. Meaning after some time, this is how it would look. The rod would become like this. The insect must have come somewhere here, where x is the distance traveled by the insect, and this is the theta. And this rod is still going with omega constant. So something is happening with the insect. So find the speed of the insect as function of theta and x. We have a rod of mass m length L. Initially it is horizontal. The insect starts walking with speed u. The insect is walking in such a way, the rod is rotating with constant omega. Gravity is there. Find the speed of the insect as function of theta and x if the rod rotates with constant omega. What's happening? Take a minute. What's the catch? The catch is this. The equation is wrong. So after theta here, if you draw the FBD, rod का weight mg, insect का own weight small mg, If you look at the perpendicular distance here, this guy would be x cos theta. So we have torque about the hinge is mg L by 2 cos theta. This is for the rod, plus small mg x cos theta. This is for the insect. But I know torque is nothing but I d omega by dt plus omega di by dt. Torque is not I alpha. Here moment of inertia is changing. What is moment of inertia of the system? Here moment of inertia of the system is I of the rod plus I of the insect. As the insect is walking, it is increasing the moment of inertia of the system. So this is ml square by 3 plus mx square. So di by dt will be 2mx dx by dt, which is nothing but speed u. This is just like a variable mass system. We have a variable moment of inertia. And we know torque equation is I d omega by dt, which actually becomes I alpha if I was constant, and omega di by dt, rate of change of angular momentum. So here this term was 0. This was omega 2mxu. So this will become 2mx omega u is equal to g cos theta ml by 2 plus small m. Solve this, you'll get u as an answer. Check it out. For people who, some of you just came, this is the formula that we used actually. Torque is rate of change of angular momentum, L is I omega, differentiated product rule. This is what we get, and if I is constant, we get torque is equal to I alpha. Just like F is equal to ma is valid only when mass is constant. If mass is variable, you have to use m dv by dt plus v dm by dt. Same thing here also. If moment of inertia is changing, you can't use torque is equal to I alpha. That's what was happening here. The insect is moving in such a way, the rate of change of moment of inertia is becoming equal to the torque thing. Alpha is 0. Clear? Easy but conceptual. Clear? Let's see one more. Now we have calculated angular momentums. We have seen this. Now we are slowly entering into conservation. Let's start with an easy one and then we'll bump it up. Turn in the page. So we have sun here. We have a comet which is going around the sun. Due to sun's gravity. Under the influence of sun's gravity. At this point, the speed is v1. This is your farthest point. And this distance is r1. Here the speed is v2. This distance is r2. This is the closest point. Find v1 by v2. Comet is going around a sun in an elliptical orbit. At the farthest point, the speed was v1. Closest point, the speed is v2. Now, when you see the words here, farthest, closest, indirectly, I gave you initial and final position, isn't it? So it is understood we have to use conservation. We have 3 conservations: energy, momentum, angular momentum. Gravitation is not, it's conservative force, you can conserve energy, but we don't use that here. Momentum you can't conserve because sun is an external force only for the particle. So you can conserve angular momentum. Think for a moment, I'll show you how to do and then we'll do more. See, the idea here is tell me one thing. When this guy is going, the comet is going around the sun. How is the gravitational force? When the comet is here, how is the gravitational force? Towards the sun. When it is here, towards the sun. When it is here, towards the sun. Means no matter wherever the comet goes, the force is always towards the sun. Gravitational force always passes through the sun. So this is the first step in conservation of angular momentum. Find a point about which torque is zero. Therefore, torque about sun is zero. Therefore, L about sun is conserved. This is your state 1, V1, distance was R1. This is your state 2, V2 and R2. So initial angular momentum L1 is equal to L2 is M V1 R1 perpendicular distance M V2 R2. बस हो गया एक ही step था. V1 by V2 is equal to R2 by R1. Easy? Simple conservation. So the main idea is that you have to find a point about which torque is zero. If you can't find that point, you can't do anything. So to conserve energy, work should be zero. To conserve momentum, force should be zero. To conserve angular momentum, torque should be zero. And torque about different points can be different. You can't use any of these things. I didn't teach you yet. So Kepler's third law is what? That gives you what? That actually comes from angular momentum only. The second law. Next thing. Top view. We have a spring here. K. L is the natural length. One end of the spring is fixed to the ground. The other side you have a mass m, which you projected with speed u at an angle theta. So this whole setup, right? Mass m is placed on a smooth horizontal ground connected to the spring as shown. Do you think this will go in a circle? As this is going, won't the spring actually, compress, elongate, compress, along? It'll go in a pretty weird path, isn't it? Because length of the spring can change. Find the maximum elongation in the spring. This is the top view. It's on the ground, so you can ignore gravity here. So find max elongation. So one end of the spring is fixed. The other end is having a mass m, which you kicked it with speed u at an angle theta. So this will go in some weird path. I don't know what it is. Find the maximum elongation and compression. See, one hint I'll tell you. In 11th and 12th physics, right? If something is not going in a circle, something is not going in a line, and it is going in any other weird path, 99% of the time, it's angular momentum conservation. For example, here, if you see elliptical path, the reason is simple. 11th and 12th, our maths is not so strong to figure out how to solve these things. The only concept you have which can solve any weird random paths is angular momentum. If you see this also, this guy will go in some weird path. Angular momentum. You can be sure, 99% of the time it is angular momentum. This comes when you solve a lot of problems, you'll learn this by experiences. So try how to do this thing. So one thing is clear, conservation karna hai, right? Torque and force equations. I can't use torque and force here because I don't know the length, everything is messed up. You're asking maximum elongation. These are the words: max elongation, max compression, final speed, final position. You don't care what is happening in the middle. Why will u and theta be constant, God? Why will u and theta be constant? So if u and theta is constant, this will go like a straight line forever. What is the question then? Initial velocity, get it. Get me the equations, no need to simplify. The numbers are not given, so numbers will be bad. Step one. What is the step one? Is to figure out whether you have to use conservations or torque and force equations. It is clear we have to use conservations. Great. Step two. I know three conservations. Energy. Can I answer energy? Are there external forces on the system? What is my system? Particle plus spring. Are there external force on the system? Yes or no? Yes. There is a fixed point on the ground. This will generate a force. There is a force on the system. The point is fixed to the ground. There will be a normal reaction at the point which is fixed. But is that point moving? No. Therefore, work done is zero. Force is there, but it is not doing work. Therefore, energy is conserved. Second, can I conserve linear momentum? No. Why? There is a force. देखा? वो important है इसलिए. If you don't figure that out, you won't get it. Third, can I conserve angular momentum? About which point? About this point. Why? The spring force is always passing through this. So torque is zero about that fixed point. Did you see how we figured out? So I can conserve energy, I can conserve angular momentum. वो idea था. That is how you should know which conservation I can use. Then you're done. Draw the final diagram. This is u, this is theta. This, let's call it O, the fixed point, and this is length L. At the maximum elongation, let the length become L plus x, and the velocity is v. Can someone tell me why the speed velocity should be perpendicular to the spring at maximum elongation? At maximum elongation, why should the velocity of the particle be perpendicular to the length?
Sir, because the length is not increasing anymore, so the velocity component should be perpendicular.
So reverse. So if you had a component, means what? The spring will still continue to stretch, right? So ये maximum नहीं था. Are you getting it? Are you getting the point? If there was a component along the spring, means it can still stretch further. So this is not maximum. Getting it? So component of velocity along the spring will be zero for an instant. You can't have a component along the spring at maximum. That's how you should know. State one, state two. You're done. Energy conservation. Energy in state one is equal to energy in state two. Initial energy half mu square. Spring ka compression is zero. Final energy half mv square. And the spring ka elongation is half k x square. Torque about O is zero since the spring force passes through it. No matter how much it stretches, the spring force will always pass through that. Therefore, L initial is equal to L final. M u perpendicular into L is equal to mv L plus x. Two equations, two unknowns. Solve. You'll get two answers for x. One is compression, one is elongation. It will not give a circular motion. इस point के बाद क्या होगा? After this point, right, the spring will again come inside, isn't it? The spring is pulling inside, na? So this motion will be like it is pulling and going, and it's not a circle. It is some weird path. What trajectory be kuch? It's not any standard trajectory that we know of. We can't solve that. We don't know what the hell it is. This much we can figure it out. Check out the steps. That's what I'm saying. When you know it is conservation, there are only three options you have: energy, momentum, angular momentum. You just need to figure out which one is working, draw your final diagram, conserve, finish it off. Please check your steps. Anyone not clear with the steps, please ask. If you see, this is all conservation of particle ka kar raha hu abhi. If you see now, I was taking it everything step by step. First, we learned how to calculate angular momentum of a particle. Then we did purely rotating body. Then we did rolling. Now we are doing conservation of angular momentum for particles. Then we'll do for rotating bodies. We'll slowly bump it up. Next one, turning the page. Anyone has a doubt on this? Udyan, clear na? Yasha, got this? Anika, clear? Next one. We have a conical smooth bowl like this. Height of the bowl is h. The upper radius is r. The lower radius is r. A. Gravity is there. This is a smooth conical bowl. Then what happened? Someone took a particle of mass m and they projected here with speed u from the top. And because of gravity, this thing started spinning inside. Now, if you give enough speed, you know what will happen? If you give enough speed, this will again start going up actually. There are two things are happening here. If you observe at any instant, there are two forces which are fighting, the centrifugal force and the gravity. If you come down, won't the speed increase? So if your speed increases, centrifugal force will dominate, you will go up. If you go up, your speed will decrease. Mg will dominate, you come down. This guy will never come out, it will be stuck there. So find the minimum speed so that it does not come out from the bottom. I don't want this thing to come out like this from the bottom. The first question. Find u minimum if the particle does not come out from the lower opening. This is the lower opening. A mass m is projected with speed u tangentially at the topmost surface. I hope the diagram is clear, everyone. If you throw with less speed, what will happen? It'll come out like this. If you throw with too much speed, then what will happen? Even before reaching only, it will come up. So there is one particular minimum speed where it will just reach here and again starts going up. So what is the minimum speed so that this thing will not come out of this thing? And suppose if you give u 2 times minimum, find the vertical component of velocity when it comes out. So when it comes out, what is the y cap component velocity? First, let's get the first part. Anyone who didn't understand the diagram, what is happening, please ask. The reason why this happens is in terms of force, the centrifugal force and the gravity are fighting. The more you come down, the centrifugal force will dominate. If you go up, speed will decrease, mg will dominate. That's the reason it is stuck between these two, upper and the lower. Upper radius is r, lower radius is a. Should I help you? Again, I'll tell you, see, when you see a question, see, this is very important. Most of you think, right, my concepts should be good. It's not only about the concepts. You should know how to solve problems also. How do you see, when you see something totally new or something weird, how do you actually handle yourself and how do you proceed? It is like, I told you this thing. It is like reading a book on how to read a book. You're getting it? That's an art. How to read a book is an art. Again, it depends on the book. If you're reading a science book where you have to absorb knowledge, there's a way to read. If you're just reading a novel and you're bored of it, but you want to finish it off, there's a way to read. Right? If I have to read a novel, right, for some reason, first of all, I throw the book out if I don't get interested after a few pages. But for some reason, I feel like I should finish it off. I start skipping almost five pages and start reading. Right? I'll keep reading till I understand the story. Let's say I skip 5 pages, I read. If I still understand the story, I'll keep going ahead. The moment I don't understand, then I'll go back and read one more page. Then I'll see if I understand. So if there's a book of 300 pages, right, most of the book is just fillers only. If you're just, and the same thing you can do with movies also. Most of the movies are crap. You can finish off in 20 minutes. You understand the basic outline. Right? So that way. So when you see a question, right, the most important thing, right, how are you even thinking about the question? So first thing, when I see the question, it is understood. You're saying you're starting from here, you're coming out from here. That is the first word that hits me. Conservation, doubt in nahi hai. Done. Second thing, if I have to use force and torque equations, do I know how this angle is going and all? It looks very complex. Now I have three conservations: energy, momentum, this thing. So are there any forces on this particle? Yes. Don't say always no. There are. There's an mg. There's a normal reaction. Two forces are there. Mg, chalo uska problem nahi hai. Mg is vertical. That does not dissipate energy. Normal is there. But normal will not do any work. Why? It is perpendicular to displacement. So there are no external force on the system. Energy is conserved. Second, angular momentum is conserved about which axis?
To the center of the.
About the central axis. But इसमें एक catch है. So let me ask you this question: is the torque zero? This will be a pretty good advanced question. They'll ask you this: is the torque zero? Is the torque on the particle zero? Yes or no? See, torque on the particle is not zero. If you look at the forces here, normal reaction, mg, you can resolve this into components, nx and ny. So if you take about the central axis, torque about the axis is zero. You getting it? Torque about the axis is zero. Why? Because nx passes through axis. Ny and mg create torque in a different plane. mg n का torque कैसा होगा? ऐसा है ना torque. It is out of the plane, isn't it? There is a torque on the particle, but it is not about this axis. It is about a different axis. See, if I take torque about this point here, how is this mg ka torque? Isn't it this way? K cap na out of the plane, isn't it? So there is a torque on the particle, but about this axis there is no torque. Are you getting this catch? You know what case is this? When we did torque in the beginning, where was that? It's not there. Okay. So here they create torque out of the plane. So be careful. That will be the statement. Is the torque zero? Torque is not zero. But torque about the axis is zero. If you see this is mg, this would be like this, out of the plane. So torque about the axis is zero. So L about the axis is conserved. You're done. So this guy is speed u, mass m. So at the bottommost point, when it is coming, let the speed be Vx and let the speed be Vy. So here Vy is zero because you want minimum. Energy in state 1 is equal to energy in state 2. Half mu square. Height of the cone was h. This is equal to half mvx square. Conservation of angular momentum. Mur is equal to mvx into a. Two equations, two unknowns, so I'll get Duke answer from here. Right, Aditya? That would be root over 2gh by r square by a square minus 1. What will you do in the second part? Second part, the difference would be same thing. Energy in 1 is equal to energy in 2 half mu square mgh half mvx square plus vy square. बस वो vy extra component आएगा अभी. Angular moment change. Mur is equal to mvx. Angular momentum will always depend on the vertical horizontal. That is the only difference. Clear with the question? Udian, Rehan, comes on. Let's see one more. Turn the page. Any doubts on this? Everyone got this right? This is a standard question. We have a sphere, mass m, radius r. Rotating with omega. So due to internal forces, maybe it's a star. This thing happens a lot in stars. Due to internal forces, it compresses to half the radius. Mass remains same. Find omega dash. Easy one, get it. Now we are conserving angular momentum in rotating bodies. Yeah. So if you see, right, internal forces do not change momentum. Since forces are internal, the torque about that axis will be 0. L1 is equal to L2. I1 omega 1 is equal to I2 omega 2. 2 by 5 mr square omega square will be 2 by 5 mr by 2 whole square omega dash. So omega dash is 4 omega. Easy? Clear. Same question. Suppose if you have a rotating disk. Someone placed another disk on top of it, but half the radius and same thickness. omega dash will change. Find new omega. Clear? Get this. Both are similar models. नहीं आ रही. नहीं ऐसा रहा हूँ. God, Ali, when you put more mass, it will slow down. Why is your disk rotating faster? You have created an infinite energy source. We need you for the progress of humanity. Yeah, Anika, that is wrong. Anyone who can create energy out of nothing, you guys are the beacons of hope. You guys are the answers for the space-time travel. नहीं Arjun, wrong. Why are you guys goofing up? Moment of inertia. अच्छे से करो ना. It is wrong. All are wrong.
So the mass of the added disk is the same, or
How do I know? I don't know. You have to figure it out. मैं सब बताऊंगा तो क्या करोगे?
figured it out, but then answer should
Nah, then why did you get answer wrong? Then Yasha got it right. What is the moment of inertia of this? So L initial m r square by 2 omega. Since the disk its thickness is same, mass will be m by 4. Mass depends on the area. Pi r square into thickness. So L final. This is the moment of inertia, everyone. The big disk will be mr square by 2 plus the small disk will be mr square by 2, but m became m by 4. R became r by 2, and this is 2. This is your moment of inertia. Check it out. So L initial is equal to L final. How much is that? 1 by 16. Omega dash is 16 by 17 omega. Check. Same thing, Anika. You created extra energy. This is your final moment of inertia of the system. I can even ask you loss of energy also. Loss of energy will be kinetic energy initial minus kinetic energy final. That you can calculate from half I omega square. Have a look at this. Let's see. Let me show you something.
This is a demonstration of the conservation of angular momentum. I have a couple of, looks like 5-pound dumbbells in my hands. I've got a platform that spins freely on its axis. I'm going to stand on this platform and then have my able assistant, David, come over and give me a spin. And then what I would like to do then at that point, I'm going to start with my arms out and then see how close I can bring the weight into my chest. Okay?
Can you see the difference
You can
there?
see
When
my
he brings
tongue
them
flying out.
closer, rotates faster.
So ice skaters use this principle. They start off in going to their triple toe loop with their arms far apart or away from their bodies.
Basically, what
They
was
bring
happening
their
now, when he
arms in
was
close and their legs
keeping
in
the
close
dumbbell
to their
far, I
bodies.
is more, omega is less. When he's bringing them closer, I decreases and omega increases. Look at this one. This is a very good one. This explains a lot. I'll post this in the group, don't worry. There, we have a student table which can rotate dumbbells. So, hands are spread apart, so I is more. He's rotating. So, if there is an omega, there's an I. Now, bring the dumbbells close. दिख रहे हैं? Omega is increased. So I1 omega, I into omega is constant. So if you increase I, omega decreases. I decreases, omega increases. You can clearly see that thing. But if you try to explain this in terms of forces and torques, it goes very weird to explain. That's why I said angular momentum is a little weird. This is an interesting one. See. Now see what happens here. And now see, the girl is standing there with that cycle wheel, okay? Initially, everything is at rest. So what is initial angular momentum? 0. Now, the moment she rotates the wheel will have an angular momentum in the upward direction. But total system ka angular momentum kitna hona chahiye tha? 0. To compensate, the girl will rotate in the opposite direction. Now observe something happens, see. Now she'll rotate the wheel 180 degrees and look at the girl, what happens to her. Now she'll rotate in the other direction. Because here, initially the system was at rest, angular momentum of the system is 0. So if the wheel is rotating k cap, the girl should rotate minus k cap. So that the total angular momentum is still 0. The moment she rotated the wheel 180 degrees, wheel ka angular momentum changed. To compensate that, the girl started rotating in the opposite direction. Now if she makes it horizontal, she comes to rest. Why? Because there's no vertical angular momentum. The girl also comes to rest. Almost. So. Now look at this thing. Now it is reverse. The girl is at rest, the wheel is rotating. So the teacher gave the wheel to her. So system ka angular momentum hai, which way upward because of the wheel ka rotation. The girl itself has no angular momentum. Fair enough. So the angular momentum of the system is girl plus the wheel. Girl is at rest, the wheel is rotating. Now see what happens. If you stop now, if you rotate the wheel, the girl starts rotating. Because the angular momentum direction changed. So to compensate, the girl started rotating in the opposite direction to keep the total L bar constant. Is that making sense, everyone? Now if she rotates the wheel again, she stops. See. Again she rotates. Basically, system ka net angular momentum should be upward, isn't it? If you put the wheel in this direction, angular momentum kis taraf hoga abhi? Horizontal. So here the girl becomes a counter thing, to generate whatever is extra angular momentum you need. देखो diagram में कैसे initially left hand can you see only L1 is up. When the wheel is rotated down, L1 goes down. To compensate, the girl will rotate with L2. So L2 minus L1 total will be L1 again. The total angular momentum should be in the upward direction. Is that making sense? So if you mess with the wheel, the girl will rotate to compensate for that. This you'll understand more clearly. Dekho. Same thing. Girl is at rest, the wheel is rotating. So she's catching it. Now the angular movement of the system is girl is at rest, wheel is upward. Now see what she does. She stops the wheel. The girl rotates. Because abhi wheel ka angular momentum 0 ho gaya, but to compensate the girl will rotate. Making sense? This is the problem we did right now. Disk is rotating, you keep one more disk on top of it. That is a computer program. It is showing omega with time. Thoda friction hai, so it is slowing down. You suddenly put on top of it, the omega drops. So this is the I1 omega 1 is equal to I2 omega 2. And there are. This is also interesting. This is that wheel ka thing which we saw. The wheel is rotating, you hang it only on one side. You don't need a second support. It remains horizontal. Because the mg is used to change the angular momentum direction instead of falling down. This is called a gyroscopic precision. Question में नहीं है, but इतना idea होना चाहिए. You can see this in another way. Look at this. This I'm sure you must have done in the park merry-go-round. So this guy is pushing, rotating. So if he just stands normally, it takes 3.2 seconds. Now if he goes to the center, see what happens. Rotation speeds up. It takes less time. 2.3 seconds. Now if he goes to the edge, moment of inertia increases. The whole thing slows down. Clearly it is slowing down and speeding up. It takes 4.13 seconds. So time has gone up. Clear with this? So there, this is what I was saying. Angular momentum, right? Mathematically, it makes sense, but once it comes to, if you try to explain in terms of, see, we humans, right? We understand forces and rotations. Energy भी फिर भी थोड़ा समझ में आता है, momentum also समझ में आता है, but angular momentum goes out of the thing. The first reason being it's a pseudo vector. Direction proper नहीं है. It does very weird things you can't explain. Let me show you one more very weird thing. This one, I guess.
What happens when you put a ball on a turntable and then start?
Where are you? Where are you? It is there somewhere. I lost it, I guess. I lost it. I'll show you next time. Okay, so that is there. So with that, we'll wrap up. So next class, when we catch up, right, we'll continue with this. We're going to do more better problems of angular momentum. So mostly next class, we'll try to wrap up the chapter. Kuch bhi thoda bach gaya, to 1 or 2, we will see it on next week. So next week, we'll finish all the chapter here. So make sure to go through the entire thing. We have done almost 68 problems so far. So do finish it. I think we will touch 80. So those are out. Stay back and ask. Also free to leave. So I'll see you guys again on Wednesday.